Methane, the mysterious and powerful greenhouse gas, ladies and gentlemen. Did you know that methane is about 25 times more powerful as a greenhouse gas than carbon dioxide? Under low temperatures and high pressure, it combines with water to form methane hydrate, a solid that looks like ice and lies beneath the ocean floor in massive deposits. In this form, an astonishing minimum of 1,800 gigatons of carbon is stored. Some scientists even suggest that this number could exceed 20,000 gigatons. For comparison, since the beginning of industrialization, the amount of carbon released from fossil fuels is just 475 gigatons. This makes the potential of methane hydrate incredibly large and equally dangerous. The fragility of methane. Methane hydrate is fragile. It can break down into methane and water if the temperature rises. When this happens, methane gas escapes from the sediment in what's known as methane leaks. Scientists are worried that climate change could increase methane emissions, which would, in turn, amplify the greenhouse effect. This could accelerate global warming and exacerbate the devastating impacts of climate change. However, it's still not possible to definitively state the magnitude of this a scientific detective story. Uncovering the past researchers from the University of Hamburg and Shanghai Ocean University, led by Jens Fiebig, are working to solve this mystery. Fiebig explains, looking into the past might give us some answers. The Earth has experienced long, warm periods in the past, but it's still unclear how much methane hydrate deposits destabilized during these times and what effect this had on gas emissions. The magic of clumped isotope thermometry. This is where the method of clumped isotope thermometry comes in. This technique measures how much heavy isotopes of carbon and oxygen group together in carbonate minerals. Microorganisms use methane as an energy source and live in the ocean sediments covering methane hydrate deposits. Carbon then becomes mineralized in solid deposits of carbonate. Carbonate minerals contain different variants of both carbon and oxygen, known as isotopes, which vary in mass. Dr. Philip Staudigl states, clumped isotope thermometry measures how much heavy isotopes cluster together in carbonates. This clustering helps us calculate the temperature at which the mineral formed and distinguish the contributions of non-thermal effects. He continues, we demonstrated that these non-thermal effects include the fingerprint of microbial communities and the methane flux that supports them. The secrets of microbial communities. These microorganisms use methane as an energy source and live in the ocean sediments covering methane hydrate deposits. During this process, carbon becomes mineralized in solid deposits of carbonate. Carbonate minerals contain different isotopes of carbon and oxygen, and these isotopes differ in mass. The arrangement of these isotopes can help us understand past ocean temperatures. Implications for the future. The recorded temperatures and non-thermal information can be used to reconstruct how much more intense gas emissions might have been due to ocean warming in the past. This helps us understand the potential impacts of climate change and plan future measures. The more we learn about the effects of greenhouse gases and climate change, the better we can take informed actions and make effective steps towards protecting our planet.